Hello everyone. I streamed a few hours ago and now I'm streaming again. I wanted to read more chapters because I felt like it. I was feeling sleepy earlier, but now I am not. Anyways, I will just change to full screen. Uh, yeah, okay. So last stream I read about address translation and segmentation. In the address translation part, the main part they talk in the address translation section, the main part they talked about was that there is the address space. Let's say this is starting over here is 0, ending over here is, let's say, 16 KB. From the programmer's point of view, the memory in here is to relative to the address space, meaning the top part is 0, the end part is 16, the middle part is whatever. But physical address is not stored like this. Physical address is like there's space for the operating system. There is a space for the operating system, and then all of this is like a space for processes. So this and this might be an address space. So these two might be an address space, or this and this might be an address space here, and the rest is free space. So in the programmer's point of view, in our view we are viewing this as 0 and the last part as 16. But in the physical address, the starting is not 0 and the ending is not necessarily 16. It could be like 32 and 48, something like that. But address translation is like you take the address relative to here, and that will be the virtual address. Like let's say 15 15 KB. And then what the CPU has to do, or the memory management unit has to do, is basically take this virtual address. We need to make changes in the physical address, right? So we need to take this virtual address at the base address. For example, like in the actual physical address, this would be 32 KB all the way till 48, I think. 48 KB. So this address space is over here. And then when we make changes to 15, we are actually making changes to 47. But the programmer doesn't know that. The programmer sees 15, but in the physical address, it's then changed to 17 and the changes are made there. Same thing for this other address, other process too. The programmer's thinking this upper part is 0, the bottom part is however large the program is, like let's say 32. The programmer is thinking of making changes between 0 and 32, but in the physical address, the address is different. So basically, that's just what address translation is. And segmentation over here. So basically, our code has the code is written here, and then the heap, which would be expanding downwards, and then there's a stack, which would be expanding upwards, and then there's a lot of free space over here. But sometimes we don't use this free space. Like a lot of processors don't use this free space, so it's like wasted space over here. So what the segmentation is, it breaks this, and this into three different segments and stores them all separately. Instead of storing the entire address space contiguously, segmentation is like you break these three pieces and store them in different areas. And then the memory management has to do like memory management needs a base register and a bound register for each of these three segments. Like 32 KB, 48 KB is the base and bound register for this entire address. But now with segmentation, there will be a different base and bound address for each of the segments of the address space. And the next topic I'm assuming is about, so this over here is called internal fragmentation when the internal space is wasted. The next topic is about external fragmentation. So if I do this, let's say this here is the operating system. Operating system. Like let's say these three fragments get broken and they get stored all over the place. So let's say there are many processes and the segments of those processes get stored. So let's say over here, and let's say over here, and let's say over here. Let's do one more. Let's say there are six segments. This is the fifth one. Now the sixth one. Now any new process that comes in over here, it has to be broken up in very weird ways. There's no clean way to break up and neatly fit the segment in a proper location. So when there's no space for the new process, that's called external fragmentation. Uh, in this chapter, we'll take a small detour from our discussion of virtualizing memory to discuss fundamental aspect of any memory management system, whether it be a malloc library or the OS itself. Specifically, we will discuss the issues surrounding free space management. Let us make the problem more specific. Managing free space can certainly be easy, as we will see when we discuss the concept of paging. It is easy when the space you are managing is divided into fixed size unit. In such a case, you can just keep a list of these fixed size units. When a client requests one of them, return the first entry. Oh, fixed size units. Wait. Yeah. Let's assume this entire memory is free. You divide it up into fixed size memory of free spaces. And when the client wants one of them, you just return one block to the client. I think that's what it's saying. I could be wrong though. Where free space management becomes more difficult is when the free space you are managing consists of variable sized units. This arises in a user level memory allocation library and in an OS managing physical memory when using segmentation to implement virtual memory. In either case, the problem that exists is known as external fragmentation. The free space gets chopped into tiny, interrelated pieces of different sizes and thus fragmented. Subsequently, requests may fail because there is no single contiguous space that can satisfy the request, even though the total amount of free space exceeds the size of the request. So 0, 10, 10, 20, this part is used, and 20, 30 is free. The figure shows an example of this problem. In this case, the total free space available is 20 bytes. Okay. Unfortunately, it is fragmented into two chunks of size 10 each. As a result, a request for 15 bytes will fail even though there are 20 bytes free. And thus we arrive at the problem addressed in this chapter. How should free space be managed when satisfying variable size requests? What strategies can be used to minimize fragmentation? What are the time and space overheads of alternate approaches? Most of this discussion will focus on the great history of allocators found in user level memory allocation libraries. We draw on Wilson's excellent survey but encourage interested readers to go to the source document itself for more details. We assume a basic interface such as that provided by malloc and free. Specifically, void malloc takes a single parameter size, which is the number of bytes requested by the application. It hands back a pointer of no particular type or a void pointer in C lingo to a region of that size. The complementary routine void free uh, void pointer takes a pointer and frees the corresponding chunk. A malloc takes size t, the free takes a pointer. Note that the implementation of the note the implementation of the interface. The user, when freeing the space, does not inform the library of its size. Thus, the library must be able to figure out how big a chunk of memory is when handled just a when handed just a pointer to it. We'll discuss how to do this a bit later on in the chapter. The space that this library manages is known as historically as the heap, and the generic data structure used to manage free space in the heap is in some kind of free list. This structure contains references to all of the free chunks of space in the managed region of memory. Of course, this data structure need not be a list per se, but some kind of data structure to track free space. We further assume that primarily we are concerned with external fragmentation as described above. Allocators could, of course, also have the problem of internal fragmentation if an allocator hands out of chunk memory bigger than that requested. Any unasked for and thus unused space in the chunk is considered internal fragmentation and is another example of space wasted. However, for the sake of simplicity, because it is more interesting of the two types of fragmentation, we focus on external fragmentation. We will also assume that once memory is handed out to a client, it cannot be relocated to another location in memory. For example, if a program calls malloc and is given a pointer to some space within the heap, the memory region is essentially owned by the program until the program returns it via corresponding call to free. Thus, no compaction of free space is possible, which would be useful to combat fragmentation. Once you hand a pointer to a chunk of memory to a C program, it is generally difficult to determine all references to that region, which may be stored in other variables or even in registers at a given point in execution. This may not be the case in more strongly typed garbage collected languages, which would thus enable compaction as a technique to combat fragmentation. Compaction could, however, be used in the OS to deal with fragmentation when implementing segmentation. Also, what they are talking about when they say compaction is like there are all of these memory segments over here. Like we would group all of them together in one space. For example, this and this instead of having these two over here, we would have something like this, both of them in a contiguous area. So, and this third one, let's join that too. This fourth one, basically, you get the idea. Fifth, Now there's a lot of space if we need contiguous memory. And that's what they mean by compaction. Finally, we will assume that the allocator manages a contiguous region of bytes. In some cases, an allocator could ask for that region to grow. For example, a level memory allocation library might call into the kernel to grow the heap when it runs out of space. However, for simplicity, we will assume that the region is a single fixed size throughout its life. Before delving into some policy details, we'll first cover some common mechanisms used in most allocators. First, we'll discuss the basic of splitting and coalescing, common techniques in most any allocator. Second, we will show how one can track the size of the allocated region quickly and with relative ease. Finally, we'll discuss how to build a simple list inside the free space to keep track of what is free and what isn't. A free list contains a set of elements that describe the free space that remain in the heap. Thus, assuming the following 30-byte heap, the free list for this heap would have two elements on it. One entry describes the first 10-byte free segment. One entry describes the other free segment. So 0 to 10 over here, 20 to 20 and length 10 over here. As described above, a request for anything greater than 10 bytes will fail. There isn't a single contiguous chunk of memory of that size available. A request for exactly that size could be satisfied easily by either of the free chunks. But what happens if the request is something for smaller than 10 bytes? Assume we have a request for just a single byte of memory. In this case, the allocator will perform an action known as splitting. It will find a free chunk of memory that can satisfy the request and split it into two. The first chunk it will return to the caller and the second chunk will remain on the list. Thus, in an example above, if a request for 1 byte were made and the allocator decided to use the second of the two element on the list to satisfy the request, the call to malloc would return 20 and the list would end up looking like this. Address 0 to 10, 21 to 21 and the length is 9. Oh. So this 20 to 21, this byte is now given by malloc to the program. In the picture, you can see the list basically stays intact and the only change is that the free region now starts at 21 instead of 20 and the length of that free region is now just 9. Thus, the split is commonly used in allocators when requests are smaller than the size of any particular free chunk. A corollary mechanism found in many allocators is known as coalescing of free space. Take our example from above once more. Given this free 10 bytes, use 10 bytes and another free 10 bytes. Given this tiny heap, what happens when an application calls free and thus returning the space in the middle of the heap? You simply add this free space back into our list without too much thinking. You might end up with a list that looks like this. So address 10, length 10, address 10, length 10. Oh, did we free that space? Oh, yeah. Calls free 10, thus returning the middle of the heap. So address 10, length 10, address 0, length 0, address 20, length 10. Note the problem: while the entire heap is now free, it is seemingly divided into 3 chunks of 10 bytes each. Thus, if a user requests 20 bytes, a simple list traverser will not find such a free chunk. What allocators do in order to avoid this problem is coalesce free space when a chunk of memory is freed. The idea is simple. When returning a free chunk in memory, look carefully at the address of the chunk you are returning as well as the nearby chunks of free space. If the newly freed space sits right next to one existing right next to one existing, uh, right next to one or two, as in this example, existing free chunks, merge them into a single larger free chunk. Thus, with coalescing, our final list should look like this. So 0 with length 30. So header used by malloc, 20 bytes returned to the caller. Tracking the size of allocated regions. You might have noticed that the interface to free does not take a size parameter. Thus, it is assumed that given a pointer, the malloc library can quickly determine the size of the region of memory being freed, and thus incorporate the space back into the free list. To accomplish this task, most allocators store a little bit of extra information in the header block, which is kept in memory, usually just before the handed out chunk of memory. Let's look at an example again. In this example, we are examining an allocated block of size 20 bytes pointed to by pointer. The header used by the malloc library, the 20 bytes returned by the caller. In the header, they mention that the pointer has of size 20. In this example, we are examining an allocated block of size 20 bytes pointed to by pointer. Imagine the user called malloc and store the results of pointer. So pointer malloc 20. The header minimally contains the size of the allocated region. It may also contain additional pointers to speed up the allocation, a magic number to provide additional integrity checking and other information. Let's assume a simple header which contains the size of the region and a magic number like this. Okay, magic number is for some security checks, I think. The example above would look like what you see in figure 17.2. When the user calls free pointer, the library then uses a simple pointer arithmetic to figure out where the header begins. After obtaining, wait, hold on, what's happening here? Free pointer, pointer minus 1. So the size of the header is fixed, right? Like every time we make a new memory, the header is a fixed size. Yeah, the header is always the same size, right? Header t, int size, int magic. And then you go back one space. By one space, I mean one size of the struct. After obtaining such a pointer to the header, the library can easily determine whether the magic number matches the expected value as the sanity check and calculate the total size of the newly freed region via simple math. Note the small but crucial detail in the last sentence. The size of the free region is the size of the header plus the size of the space allocated to the user. Thus, when a user requests n bytes of memory, the library does not search for a free chunk of size n, rather, it searches for a free chunk of size n plus the size of the header. Okay. Embedding a free list. Thus far, we have treated a simple free list as a conceptual entity. It is just a list describing the free chunks of memory in a heap, but how do we build such a list inside the free space itself? In a more typical list, when allocating a new node, you would just call malloc when you need space for the node. Unfortunately, within the memory allocated library, you can't do this. Instead, you need to build the list inside the free space itself. Don't worry if this sounds a little weird. It is, but not so weird that you can't do it. Assume we have a 4096 byte chunk of memory to manage. To manage this as a free space, you first have to initialize set list Initially, the list should have one entry of size 4096. Here's a description of a node of the list. So struct node, integer size, and then the next node. So basically it's just a linked list, right? Now let's look at some code that initializes the heap and puts the first element of the free list inside that space. It is assuming that the heap is built within some free space acquired via a call to the system call mmap. This is not the only way to build such a heap, but serves us well in this example. Here's the code. Mmap returns a pointer to a chunk of free space. Header. So size of node t. Or this size is what the head is taking. Head next is null. Okay, I need. After running this code, the status of the list is that it has a single entry of size 4088. Yes, this is a tiny heap, but it serves as a fine example for us. The head pointer contains the beginning address of this range. Let's assume it is 16 kilobyte. Visually, the heap looks like something. Looks like what you would see in figure 17.3. A heap with one free chunk. Heap. So all this space is this many size. And the next is 0. It's not 4096 because the header itself takes some of the size. Now let's imagine a chunk of memory is requested, say the size of 100 bytes. To service this request, the library will first find a chunk that is large enough to accommodate the request. Because there is only one free chunk, this chunk will be chosen. Then the chunk will split into two, one chunk big enough to service the request, and the remaining free chunk, assuming an 8-bit header. The space in the heap now looks like what you see in figure 17.4. So we have 100 bytes now allocated. Oh, wait. Okay. So this here is the free space. This here is 100 bytes now allocated for some process. Thus, upon the request for 100 bytes, the library allocated 10 byte. Out of the existing one free chunk. It returns a pointer to it, stashes the hidden information immediately before the allocated space for later use upon free, and shrinks the one free node in the list to 3980 bytes. Now let's look at the heap when there are 3 allocated regions, each of 100 bytes. A visualization of this heap is shown in figure 17.5. So heap, there's one address space here, one used space here, one used space over here. Okay. As you can see therein, the first 3 to 4 bytes of the heap are now allocated, and thus we see 3 headers in that space as well as 300 byte regions being used by the calling program. The free list remains uninteresting, just a single node, but now only 3764 bytes in size after 3 splits. But what happens when calling program returns some memory via free? In this example, the application returns the middle chunk of allocated memory by calling free 16500. So I'm guessing this S pointer gets freed. Oh, but about to be freed. Okay, this part gets freed. The value of 16,500 is arrived upon by adding the start of the memory region 16,384 to the 108 of the previous chunk and the 8 bytes of header for this chunk. This value is shown in the previous diagram by the pointer as pointer. The library immediately figures out the size of the free region and then adds the free chunk back onto a free list. Assuming we insert at the head of the free list, the space now looks like this. So this is used up, this is used up, this is free, and this is free. Now we have a list that starts with a small free chunk, 100 bytes, and a large free chunk, 3,764 bytes. Our list finally has one more element on it. And yes, the free space is fragmented but an unfortunate but common occurrence. One last example, let's assume now that the last two in use chunks are freed. Without coalescing, you end up with fragmentation. As you can see from the figure, we now have a big mess. Why? Simple. We forgot to coalesce the list. Although all of the memory is free, it is chopped up into pieces and thus appearing as fragmented memory despite not being one. The solution is simple. Go through the list and merge the neighboring chunks. When finished, the heap will be whole again. Hold up. Do they refer to figure 17.7? You would end up with fragmentation. So here's a used up size. Here's a used up size. This is free. This is free. But the solution is simple. Go through the list and merge the neighboring chunks. When finished, the heap will be whole again. Why are they all now free? Oh yeah, and this is size 100 and it has a next for this address which is pointing to here. We should discuss one last mechanism found within many allocation libraries. Specifically, what should you do if the heap runs out of space? The simplest approach is just to fail. In some cases, this is the only option, and thus returning null is an honorable approach. Don't feel bad. You tried, and though you failed, for a good fight. Most traditional allocators start with a small sized heap and then request more memory from the OS when they run out. Typically, this means they make some kind of system call, break in most Unix systems, to grow the heap and then allocate the new chunks from there. To service the break request, the OS finds free physical pages, maps them into the address space of the requesting process, and then returns the value of the end of the new heap. At that point, a larger heap is available and the request can be successfully serviced. Now that we have some machinery under our belt, let's go over some basic strategies for managing free space. These approaches are mostly based on pretty simple policies that you could think up yourself. Try it before reading and see if you can come up with any alternative. Come up with all of the alternatives. The ideal allocator is both fast and minimizes fragmentation. Unfortunately, because the stream of allocation and free request can be arbitrary, any particular strategy can uh, can do quite badly given the wrong set of input. Thus, we will not describe the best approach. a best approach, but rather talk about some basic and discuss their pros and cons. The best fit strategy is quite simple. First, search through the free list and find chunks of free memory that are as big or bigger than the requested size. Then return the one that is smallest in that group of candidates. This is so-called best fit chunks. One pass through the free list is enough to find the correct block to return. Okay, so what I'm understanding is that if we have a process where the address space is like so this can fit, it can fit this address space can fit here, it can fit here, but it can't fit here. So best fit is like find the one that fits perfectly in here, which is like not exactly perfectly, but the closest to its size. In this case, it would be this one. The intuition behind best fit is simple. By returning a block that is close to what the user asks, best fit tries to reduce wasted space. However, there is a cost. Naive implementations pay a heavy performance penalty when performing an exhaustive search for the correct free block. The worst fit approach is the opposite of the best fit and the largest chunk, uh, find the largest chunk and return the requested amount. Keep the remaining large chunk on the free list. Oh, so in this case, worst fit would be over here then. You find the largest chunk. Keep the remaining larger chunk on the free list. Worst fit tries to thus leave big chunks free instead of lots of small chunks that can arise from a best fit approach. Once again, however, effort search of free space is required and thus this approach can be costly. Worse, most studies show that it performs badly, leading to excess fragmentation while still having high overloads. The first fit method simply finds the first block that is big enough and returns the requested amount to the user. Uh, First fit has the advantage of speed, no exhaustive search of all the free spaces are necessary, but sometimes pollutes the beginning of the free list with small objects and uh, thus how the allocator manages the free list order becomes an issue. One approach is to use address based ordering. By keeping the list ordered by address of the free space, coalescing becomes easier and fragmentation tends to be reduced. Instead of always beginning the first fit search at the beginning of the list, the next fit algorithm keeps an extra pointer to the location within the list where one was looking last. The idea is to spread the searches for free space throughout the list more uniformly, thus avoiding splintering of the beginning of the list. The performance of such an approach is quite similar to the first fit, as an exhaustive search is once again avoided. Here are a few examples of the above strategy. Envision a free list with three elements on it. Sizes 10, 30, and 20. Assume an allocation request of size 15. A best fit approach would search the entire list. Find that 20 was the best fit. Oh, this is like 10 free space, 30 free space, and 20 free space. Your size 15 and 20 and 30 are candidates, but 20 is the best fit. So it's resulting in this. As happens in this example, and often happens with best fit approach, a small free chunk is now left over. A worst fit approach is similar, but instead find the largest chunk, in this example 30. So 15 is over here now. There is, okay. The first fit strategy in this example is the same thing as the worst fit, also finding the first three block that could satisfy the request. The difference is in the search cost. Both best fit and worst fit look through the entire list, Force fit only examines free chunks until it finds one that fits, thus reducing search cost. These examples just scratch the surface of allocation policies. Other approaches. Beyond the basic approaches described above, there have been a host of suggested techniques and algorithms to improve memory allocation in some way. We list a few of them here for your consideration. One interesting approach that has been around for some time is the use of segregated lists. The basic idea is simple. If a particular application has one popular sized request that it makes, keep a separate list just to manage objects of that size. All other requests are forwarded to a more general memory allocator. The benefit of such an approach are obvious. By having a chunk of memory dedicated for one particular size of request, fragmentation is much less of a concern. Moreover, allocation and free requests can be served quite quickly when they are of the right size, as no complicated search of a list is required. Just like any good idea, this approach reduces new complications into the system as well. For example, how much memory should one dedicate to the pool of memory that serves specialized requests of a given size as opposed to the general pool? One particular allocator, the slab allocator by Uber engineer Jeff Bonwick, handles this issue in a rather nice way. Specifically, when the kernel boots up, it allocates a number of object caches for kernel objects that are likely to be requested frequently. The object caches thus the object caches thus are each segregated free list of a given size and serve memory allocation and free requests quickly. When a given cache is running low on free space, it requests some slab of memory from a more general memory allocator. The total amount of requested being a multiple of the page size and the object in question. Conversely, when the reference counts the objects within a given slab all go to zero, the general allocator can reclaim them from the specialized allocator, which is often done when the VM needs more memory. The slab allocator also goes beyond more segregated list approaches by keeping free objects on the list in a per initialized state. Okay, Bonwick shows that initialization and destruction of data structures is costly by keeping freed objects in a particular list in their initialized state. Uh, by keeping free objects in a particular list in their initialized state, the slab allocator thus avoids frequent initialization and destruction cycles per object and thus lower overhead noticeably. Buddy allocation. Because coalescing is critical for an allocator, some approaches have been designed around making coalescing simple. One good example is found in the binary buddy allocator. In such a system, free memory is first conceptually thought of as one big space of size 2 to the power of n. When a request is made, uh, the search for free space recursively divides free space by 2 until a block that is big enough to accommodate the request is found. At this point, the requested block is returned to the user. Here's an example of a 4 KB free space getting divided in the search for a 7 KB block. Figure 17.8. So 8 bit, 16. Okay. 64 KB free space getting divided in the search of a 7 KB block. In the example, the leftmost 8 KB block is allocated and returned to the user. Note that this scheme can suffer from internal fragmentation as you're only allowed to give out power of 2 sized blocks. The beauty of buddy allocation is found in what happens when that block is freed. When returning 8 KB to the free list, The allocator checks whether the body 8 KB is free. If so, it coalesces the two blocks into 16 KB block. The allocator then checks if the body of 16 KB block is still free. If so, it coalesces these two blocks. This recursive coalescing process continues up the tree, either restoring the entire free space or stopping when a body is found to be in use. The reason buddy allocation works so well is that it is simple to determine the buddy of a particular block. How you ask, think about the addresses of the block in the free space above. If you think carefully enough, you will see that the addresses of each buddy only differs by a single bit, which bit is determined by the level in the buddy tree. One major problem with many of the approaches described above is their lack of scaling. Specifically, searching lists can be quite slow. Thus, advanced allocators use more complex data structures to address these costs, trading simplicity for performance. Given that modern systems often have multiple processors and run multi-threaded workload, it is not surprising that a lot of effort has been spent making allocators work well on multiprocessor based systems. Okay, guess that's the end of the chapter. Okay, I will end the stream here then. Yeah, so next time I will be studying Introduction to Paging. Okay, anyways, see you guys next time then. Bye.